Adding a methyl group to butanes gives us pentanes. So in this video, we're going to be looking at pentanes and pentyl compounds. So with pentane, there are actually three constitutional isomers. If we think about how to add a methyl group to butane, of course we have two butane constitutional isomers, butane itself and isobutane. So if we add a methyl group on the end of butane, we get pentane. Now notice, recall when we were talking about butane, butane had two different types of carbons. They had the methyl groups and the methylene groups. So I can add a methyl group to one of the methylene groups of butane, and I get an isomer of pentane, which we call isopentane. Now, there's the other methylene group, and if I add a methyl group to the other methylene group, I still get the same compound. Again, remember, thinking three-dimensionally results in identical compounds. So these are the two constitutional isomers that result from adding a methyl group to that of butane. Remember, we also had isobutane. And so if I add a methyl group to isobutane, I could add a carbon on the end, which would simply result in isopentane. And if you're not sure about that, simply draw it out and see what you get. But I can also add a methyl group to the CH, right? Replacing the H with a methyl group. And I get a new isomer. And this new isomer is called neopentane, a new pentane. See how creative organic chemists are? Now, when we think about derivatives, there are now 8 different C5H11X derivatives. And I'm showing you this to simply show, we're pretty much going to stop at pentane because, as you can imagine, the more carbons you have, the more possible derivatives you have. But one of the reasons why I want to take a look at pentane is to think about the different carbons, the different types of carbons. So here I have pentane, and pentane has 3 different types of carbons. Take a moment to see if you can figure out the 3 different types of carbons. Okay, now I'm going to show you. So the methyl groups at the end are the same. Why? Because they have the same substituents coming off of them. They have 3 hydrogens, and then they essentially have a butyl group attached to them. The 2 methylene groups are the same, again for the same reason. Each one of them has a methyl group, 2 hydrogens, and a propyl group coming off of it. But notice these 2 methylene groups are different than this methylene group. Why? Because this methylene group has different substituents coming off of it. It has 2 hydrogens, and it has 2 ethyl groups coming off of it. And therefore, it is distinct. It is different than the other 2 methylene groups. The result is that since I have 3 different types of carbons, I have 3 different derivatives of pentane, right? One in which I substitute X for a hydrogen on one of the methyl groups, right? So notice I could do it on the one on the right, like I'm showing, or I could substitute it one of the hydrogens on the left. I'd get the same thing. Then I can substitute a hydrogen on one of the green methylene groups, and I get this. Again, notice I could put it on this particular carbon or I could put it on the other green carbon. I get the same thing. And then lastly, I can place it on the red carbon and I get this derivative. And so all three of these are different derivatives of pentane. Well, pentyl derivatives, right? Now, that is using only pentane as a source of replacing the hydrogens. Let's look at using isopentane. How many different carbons do we have on isopentane? Well, the two methyl groups on the right-hand side are the same. Again, why? Because they're connected to the same thing. They're connected to 3 hydrogens and a sec-butyl group. Then I have this methyne carbon, CH. It's different than methyl groups. Then I have this methylene group that's different than the methyl groups and the methine. And lastly, I have this methyl group. Now notice it's a methyl group, but it's different than the other 2 methyl groups. Why? Because it has 3 hydrogens and it has an isobutyl group attached to it, not a sec-butyl group. And so they're different. Therefore, I have 4 different types of pentyl substituents using the isopentane as my backbone, as my carbon skeleton. I can replace one of the blue methyl hydrogens with X. I can replace the green methine hydrogen with X. I can replace the methylene hydrogen, one of the methylene hydrogens with X. And lastly, I can replace one of the orange methyl hydrogens with X. So I get 4 different ones here. So notice I got 3 with pentane. I get 4 with isopentane. How many do I get with neopentane? Well, it happens with neopentane. There are 2 different types of carbons. We have the 4 methyl groups, and then we have this quaternary carbon. Now, the quaternary carbon has no hydrogens, right? It's quaternary. Notice the spelling. It's not quaternary, it's quaternary. And because it has no hydrogens, you can't replace it with X. And therefore, you can only replace one of the methyl hydrogens, and so you get only 1 derivative out of that. So we have 3 from pentane, we have 4 from isopentane, that's 7, and then we have 1 from neopentane, that is 8. So a total of 8 different pentyl derivatives that we can get. And so you can see how things can get much more complex the larger you get in terms of carbons.